scaling algorithm, and we saw that it had dependency on C. And we were thinking that how can we get an algorithm? We were talking about how we can get an algorithm such that its running time is, it does not depend on C. It is just polynomial in M and N. Right? So that is what we'll be talking about today, and we'll be looking at what is called a preflow push algorithm. Okay. Just a moment. Okay. So in the push algorithm, what we'll have, so this is slightly different from what we had, like, in the normal Ford-Fulkerson algorithm. And here, instead of a flow, what we'll have is, so instead of maintaining a flow all the time, right? We will try to get to a flow, and we will see what that means. And instead of pushing a flow of on a path, am I audible? Is it working?
Yes, sir.
Disturbance for speaking. Let's hope this works. Okay, all right. Let's see if it works. Let me try to get to the, like, IIT Wi-Fi if it's there, but it's not even coming. So there is some problem. Hi, yes, I know there, the connectivity today is really bad. Yeah, I know screen is also paused, but now is it fine? Let's try. Okay, good. Hopefully it should work now. Am I audible?
Yes, sir. Sir, please can you repeat this 2-3 lines?
Okay, so all I was saying was that this thing is instead of maintaining a flow, we try to get to a flow. We will not maintain a flow at all times like we did in Ford Fulkerson. And instead of pushing a flow on a path, we will push flows on edges. Okay, so that is why now we'll not maintain a flow at all times and so on. So that is how it's going to be slightly different from what we had. Okay, so we'll see what these things mean. Okay, so first we'll define the concept of a pre-flow. So what is a pre-flow? Pre-flow is a function from edges to, let's say, non-negative reals, such that the first is the flow, the capacity constraint, that is the same. Okay. And the second is now slightly different. So instead of the flow conservation constraint that we used to have for flows, now we have slightly different. Now what do we have? We have that E belongs to delta plus of, or delta minus, let's say, of V. F of E is greater than or equal to E belongs to delta plus of V, F of E, right? So what does this mean? That we get at least as much in as it's going out.
Excuse me, sir.
Yeah.
Sir, I guess your screen is frozen again.
Right. Yeah. Today it's particularly bad for some reason, the connectivity. Hopefully. Okay, good. So what I was saying that, okay, so the first is the normal capacity constraint, which is the flow value, or the pre-flow value is at most the capacity. And the second constraint is that if we look at the flow that is coming in, that is at least the flow that is coming out. So get at least as much in as is going out. Right? So this should tell you that what does it mean that for every vertex, the kind of flow conservation constraint we had, that is not what we are going to have here. So it is not going to be that this F is always going to be a flow, right? So we also define something called an excess of a vertex. Of the flow F at node V. And how do we define this? This is just the difference of those two quantities, right? EF of V is equal to E belongs to delta minus V, F of V, minus E belongs to delta plus V, F of V, right? So how much is coming in minus how much is going out. So that is the excess that a vertex has. Okay. And this you can observe that a pre-flow having zero excess at all nodes, V belonging to V minus ST, because at S and T you cannot have flow conservation, is actually a flow. And with value of F is equal to minus of excess of S, EF, how did we say it? S because S, has negative axis because it does not have anything in, but it has going out. So the flow value is going to be the minus of that. And this is equal to axis of P, right? And we use GF to denote the residual graph as before. Exactly the same definition of the residual graph, the forward edges, the backward edges, and so on. And we want to now push again along the edges of residual graph. Okay, so till now we have just defined this thing called pre-flow, and we are saying that okay, we will continue with the idea of residual graph as we had before. Okay. Now there is another concept that gets added, which is called height or labeling. Okay. So every vertex is given a label, which we'll call like height. Okay. And the flow will go from higher nodes to lower nodes. By this height parameter, right? So what is this height? Height is the labeling h from vertex set to some integers, non-negative integers, right? And now we want to relate this height with the preflow, okay? So we say that a labeling h and a preflow f are compatible right? If the following two things happen. First, the height of t is equal to 0 and height of s is equal to n, right? So this is called source and sink condition. And the second one it says, which is called steepness condition. What does the steepness condition say? That if you look at for all edges, PW inside the this residual graph, or let's say EF be the edge set of residual graph. Then the height difference is at most 1. Okay, so this is always going to be V is going to be less than or equal to HW plus 1 for every edge in the residual graph. Whatever the labeling will give, the labeling should not increase the height of V by more than 1 from W, right? So these are the two conditions. So this is just, so what is the idea that, okay, we want to push the flow from higher vertices to lower vertices. So the source is at the highest, so this is like level N. And then we want to push flows, but we want to push at most one at a time, one level at a time. Okay. There is some other vertex also here. Yeah, I mean, so the book has these diagrams. It should not be here. It should more like, because these are different vertices. You might have something like this. You might have something like this also, and so on. So these are the heights, like this is -1, this is something else, and you keep pushing, and at the bottom you have this T. So this is S, this is T, and this is level 0. Right? So this is the idea. And what does the first condition say? What first condition says that T always remains at 0 if for compatible, S always remains at N. And now for any edge that is there in the residual graph, look at the two nodes, their height difference can be at most 1. So this is what the conditions are saying. All right. So, I mean, there can be a flow like this also when they are same. I mean, there can be an edge like that and so on. Here also there can be an edge like that and etc. Right? There can be like this. But the difference cannot be, there cannot be an edge like, for example, this. This is not allowed. Okay, such that the difference in height is more than 1. Okay, so is
So
that...
can two nodes have same height?
Yes, two nodes can have same height. Like here, right? These two have same height, these two have same height, and so on. Okay. Any other question or thing about this these two definitions? So first we defined the preflow, and then we defined these labelings, and then we said that preflow and the labeling are compatible if something happens.
So can there be flow between two nodes at the same height?
We are not talking about flow right now. We are talking about the edges. So there can be an edge in the residual graph between nodes at the two heights. Flow, we have not yet defined how, like, the flow values or, how those things work. We have not really put anything. So in the residual graph, of course, there can be an edge. So there can be flow that way, that, okay, this value can be non-zero. But how these things will work, we have not yet come to that how we will increase the flow and so on. Okay. Till now, it is just that given a flow and the residual graph according to that flow, what is compatibility of a labeling with that flow? Okay. Any other question? And we'll not be pushing the flow on the same way, same level. We'll talk about that. At the same height, we'll not be pushing the flow, but we'll come to that.
Sir, if we have both forward and then backward edge between two vertices V and W, then both inequalities will hold.
Exactly. So both will have to hold. That's correct. For every edge in the residual graph, this has to be true. Be it a forward edge, be it a backward edge. Okay.
Okay. Okay.
Good. Okay. Let's get ahead then. So now the thing is that if there is actually, the lemma says that if there is a preflow, F compatible with labeling H, then there is no ST path. In GF, in the residual graph. So what this is saying, that if you have a preflow that is actually compatible with the labeling H, then there is no ST path in GF. Okay. And what is the proof? So the proof is actually very easy, because the idea is this, that S is at this level, nth level, T is at 0th level. How can you reach if you don't make any jumps? Right? So in between there are n minus 1 levels, but you have only n minus 2 vertices. So I'm not actually going to prove this like, in detail. So n minus 1 levels between S and T, n minus 2 vertices available. Can't jump levels. Why can't jump levels? Because F and H are compatible, and if they are compatible, that means if you take any edge, that can move you down by just one level. Is that clear? Any question about that?
Why n minus 1 levels?
T is at 0 and S is at n. That is the condition of compatibility here. So how many levels are in between 0 and n?
Yes, okay.
Okay. So any other question about that? I'm not going to prove that in detail. I mean, it is just you just look at a path and then say that, okay, it can drop by at most one. Like this is essentially the argument. Okay, good. So now the thing is that if there is a pre-flow that is compatible with labeling, then there is no ST path in GF, right? But we know also something from previously that if there is a flow such that there is no path in GF, then we know that the flow is maximum, right? In the previous class, we had seen that was the stopping condition of the Ford-Fulkerson algorithm, right? So now what the lemma can be that if there is an ST flow compatible with labeling H, then F is a maximum flow. Right? And the proof is from the, so proof, since it is compatible, again, no ST path in GF, and that's why max flow. Why? Because this is a flow. This is not a pre-flow. This was a pre-flow in this lemma. Okay. So that gives us an idea that, okay, how do we go about it now? So we start with the pre-flow and always maintain a labeling that is compatible with the pre-flow. Okay, so there is never an ST path in the residual graph. But slowly what we'll do, we'll try to convert this pre-flow into a flow. And finally, when we are able to convert this pre-flow into a flow, then again, we have a compatible labeling because that's what we have been maintaining inductively all the times. So finally, we have a residual graph in which there is no ST path, but now we have a flow. So whatever we get is a maximum value flow. Okay. Any question about that? So actually, the argument might sound convoluted, but it is not really. So if you have any question, please ask. Okay, so I mean, so what happens in Ford-Fulkerson? Maintain a flow at all times. And here in pre-flow push, maintain pre-flow. And compatible labeling at all times when when it becomes a flow, optimality follows. Okay, so this is going to be the idea that, okay, here we will have a pre-flow, we'll maintain a labeling, and then we'll keep trying to make it into a flow. And when it will become a flow, since we are always maintaining a labeling that is compatible, the optimality will follow because of these two lemmas. Okay. Any questions? Okay, if not, then let's see how the algorithm works, right? So first it initializes HV is equal to 0 for all V belongs to V minus S, and HS is equal to N. So it gives the source the height N, and everything else it gives the height 0, right? But now we need to have a preflow that is compatible with this labeling. So how can we get? What does this mean? That, HV has height 0, but HS has height N. What does that mean? In the residual graph, what can we say about some edges? Can we say something that some edges should exist, some edges cannot exist, and so on?
So no edges can exist, right? Because the difference is greater than 1.
No edges can exist between what?
So between S and any other vertex.
Yes, exactly. So no edges can exist. So in GF, no edges can exist in, let's say, delta plus S, right? And how can we achieve this? What kind of flow values if we give that these edges will not exist in GF?
So giving them maximum flows, H
Exactly.
capacities.
Yeah, capacities, right? So we put FE is equal to CE for all E belonging to delta plus of S, right? And FE is equal to 0 for all other E. Fine. So this is compatible. You can now see that these two are compatible. Okay, good.
So
So
what
now
about back edges?
you can think about it. So back edges also between any other things is fine, right? And the what does the condition say? Condition says that if there is an edge VW, then V's labeling should be less than or equal to HW plus 1, right? So if there is a back, right? So if there is a back edge to S, then the labeling of the vertex from which there is an edge should be less than or equal to the labeling of S plus 1, which is fine, right? So you can verify this actually, that F and H are compatible. Okay, good. So the question is now, how does the algorithm work? So this is just the initialization, right? So the idea is, So as I had said, convert F into a feasible flow. And have compatibility throughout. Okay, this is the main idea. So how can we convert it into a flow? We had this condition that when is a preflow of flow? Here, this, right? That if a preflow has zero access at all nodes, then it is a flow, right? So what should we do? We look at the nodes which have positive access, and then we try to push something out from there, right? So consider V in V such that excess of F of V is greater than 0, right? The excess is greater than 0, right? And if there exists some VW in the edge set of the residual graph such that H of W is less than H of V, then we modify F to push some flow on VW, right? So what is the idea? That, okay, you have this vertex V and you have this vertex W, there is height difference, and V has some excess. It has more coming in than it has going out. So then we put some flow on this, right? So that is the idea. Okay. So let's see what we mean by that in the in actual algorithmic terms. So what are we saying here? We are saying that push F, H, V, and W. So F is the flow value, H is the labeling, V and W are vertices. And this is applicable if axis is greater than 0, the height of W is less than height of V, and VW is an edge in the residual graph, right? So if VW is a forward edge, right? So if V is here, W is here, and if this is a forward edge, if this edge is a forward edge, then we need to increase the flow basically. So remember from earlier thing that if it is a forward edge, then we increase the flow. If it is a backward edge, then we decrease the flow on that edge, right? On the edge in the graph for which it is a forward or backward edge. Okay, so if this is a forward edge, then we look at, so this is E, right? So then we look at that, okay, which of the quantities we can, where will we hit the ceiling first? So we should not be pushing more than, so even if the capacity of E, so maybe E has capacity C, even if the capacity is more, we should not be pushing too much such that the capacity gets violated. We don't want to violate the capacity constraint, right? So we want to remain below the capacity, right? So CE minus FE should be there. We should not be pushing more than this. Also, we should not be pushing more than the excess. We should not be just reaching CE while there is no incoming flow to V, for CE, right? So we take the minimum of these two, that, okay, how much is excess that V has and how much capacity does this edge have? How much more capacity does this edge have? And we increase FE by that amount, right? For a forward edge. Now for a backward edge, what is the case? So if this was a backward edge, if VW was a backward edge, right? So that means, So VW is a backward edge, let's say, and actually this was the forward edge, WV, right? So this is E actually now. E is equal to WV. And now how much you can push back here, that is, EFV. Sorry, FE is how much you can push back here. And how much is the excess that we have? Excess is this much. So this is the edge on which you have flow value FE. And that is why this backward edge is there, because you can push back FE units of flow on the edge E. And so basically you can decrease the flow by FE, but you should not be decreasing the flow by more than what V has access. So that is why you take the minimum of FE and EFV and decrease FE by that delta, right? So any question about this, about the push operation? We'll come to other operations, that how do we find out, how do we go about, which is this edge and so on. But if these initial conditions are satisfied, that excess is greater than 0, the height is different, and also the height is different, but it cannot be different by more than 1 because of the compatibility condition that we had earlier. So this also implies h of w is actually equal to h of v minus 1. Okay. And then finally we return this new flow, f and h. Okay. Any question? So, I mean, the idea is not very hard, that we have this vertex V, it has more flow than incoming, we want to push out. And we want to push out we can only push out to vertices which are below it. Okay, so look at all the vertices which are below. They can be exactly one. Yeah.
Sir, above when we were defining the initialization, and we said that source is n and all of the other vertices are 0, and then we pushed the maximum flow on all the neighboring vertices. So did that not create a back edge where the difference between heights was more than 1?
This question was asked by Mrityunjay before, so you should pay slightly more attention. So what does the condition say? The condition says that if there is a edge VW in the residual graph, so here the edge will be in the form VS, right? Amit?
Yes, sir. Yes, sir.
Yeah. The back edge that you're talking about, right?
Yes, sir.
In form of Vs. So what does it say? H of V is less than or equal to height of S plus 1. So it is only in one direction, the inequality.
Okay, sir. So only the first. Okay. So it does not have to hold the other way around.
Yes. Okay. So you can have edges like backward edges, from bottom to up, which jump. That is fine. But from up to bottom, you cannot have edges that are jumping.
Okay, sir.
Okay.
So here when h of w in this algorithm we say less than h of v. So if it's in the case of backward edge, then hw is equal to hv minus 1 is not necessary.
Yes, so that is why we are going to look at HW is strictly less than H of V. So if HW is strictly less than H of V and VW is an edge, then this has to be true, right? Because of the condition.
Okay, sir, right. It's okay.
Right. Because this is an edge, VW is an edge. And H of W is less than H of V, then if you apply the condition, then it has to be true. Because what the condition say that H of V is less than or equal to H of W plus 1, right?
Okay. Right, sir.
Yeah. Any other question? So today I'll just try to complete the description of the algorithm, and in the next lecture we'll complete the analysis. But is the operation clear now? That okay, now we have an actually, I would want to do this like quickly. I don't want there to be too much gap. So by Tuesday, maybe you guys will be very would have forgotten everything. So is there a time over the weekend that I can take one?
Tomorrow is Working as Friday.
Oh, tomorrow is working as Friday. Thank you very much. That's very good. Thanks for reminding me. So tomorrow we'll have the class at this time then. Good. Thank you, Saransh. Good. Then there will not be gaps. So all right. Good. I had forgotten about that. Thanks. So all right. This is fine, right? That what is the push operation? Push operation is we look at a vertex V and which has some axis and try to push as much of the axis as we can if there is an edge to a lower level, to some W at the lower level, right? Good. But now, like, what if we can't find such a thing? Like initially, whatever the condition is, there is nothing to like, so all the vertices which are V initially, remember, initial S is above and everything else is at level 0. And all of them have access. I mean, all of them have access because they have, this incoming flow, but they don't have anything outgoing, right? In terms of F. In the graph, they have back edges, but in terms of F, they have these things, right? That they have incoming flow, but they don't have any outgoing flow. So they have access. So what do we do? So the point is that if we can't push excess flow out of V, then we increase the height of V. Okay, that everything that we are seeing going out of V is already either at the same level or above. Then we have to increase the height of V, right? So that is the procedure relabel. So what does relabel do? Relabel does FHV, and it is applicable if the excess is greater than 0 and for all edges in the uh, residual graph, we have that the height is either same or above height of W. And then we increase the height of V by 1. Okay, so this is the relabel operation. This is it. And this basically now is the whole algorithm. Okay, so let's look at the algorithm. What does the algorithm do? Algorithm says that initially HV is equal to 0 for all V not equal to S and HS is equal to N, that we have already seen, that we do this. Now F is equal to C for all E in going out of S. F is equal to 0 for all other edges. This also initialization condition we have seen, right? Now that's all. While there is a node V not equal to T with excess greater than 0, let V be that node, right? Now, if there is a W such that the push can be applied, then we push. Otherwise, we increase the height of V. And that's it. That's the algorithm. Okay. So initially, we start with some initial conditions with some pre-flow, and that pre-flow is just pushing out on, like from S, it pushes out on every possible edge, whatever the capacity of the edge is. We start from there. And then we apply this. We look at a vertex which has excess. We try to push. If we cannot push, then we increase the height of V. Okay. So is the algorithm clear? So the analysis is going to be a little bit intricate, but we'll come to that tomorrow. But is there any question about the algorithm? So the push operation, just to remind, push operation has these two cases, forward backward edges, and there we have these that okay, in one case the capacity gets fulfilled, and the other case the excess gets removed, and both of them will have to analyze carefully while analyzing the algorithm. So we'll see these things in detail. That how this works. But there is one thing that is clear, that the algorithm, if we can show that, okay, so just one small thing. If we show that H is compatible to F at all times implies correctness of algorithm. Why? That it gives a maximum flow. Why is that correct? And actually, I'm not going to show this. This you can observe, like, by yourself. But if we show that, or if we believe that H is compatible to F at all times, then I claim that the algorithm is correct. It gives out the maximum flow. Why is that the case? When does this while loop terminate?
When it becomes a flow.
Yes, when no vertex has an access, and which means when it becomes a flow, and when it becomes a flow and we have a compatible labeling, then we saw that there is no ST path, and if there in the residual graph, or the flow is optimal, right? So when it becomes a flow, then we know that the optimality condition will be satisfied because we are having this compatible labeling all the time, and there will be no ST path in the final graph in GF. Right, so that is why that implies the correctness, that this F that is returned is the max flow. Okay, so the correctness is not very hard to see. Now you have to, so see for yourself that H is compatible to F at all times. So you have to see that, okay, whenever F changes, so here nothing is changing, but here you are relabeling this. So it is not very hard to see actually in relabel operation at least, because you are increasing HV by 1. And when are you increasing HV by 1? When H of W is greater than or equal to H of V anyway. So everything is here, or, so V is here and everything is here or above. Now, if V goes 1 above, then for all the outgoing edges, no steep coming down edges are going to be there. Right? Steep going up can be there, but there is no steep coming down edges coming out of V. So here, if it was compatible before, then it is compatible now. And similarly for push also, you can see, because the height is not changing really of any pair of vertices, it will remain compatible. It's not hard to see, but I'm not going to argue that. So this is, you can see for yourself. So one case I have already done for relabel, that V is here. Okay, I'm not going to repeat it again. Okay, you can see it if you want later. So good. So now we know the correctness, and all now we need to show is that, okay, how much is the running time, and so on. That how many times these push and relabel operations are going to get performed, etc., etc., and that we'll see tomorrow. Okay. So any questions about the algorithm or anything? I'll be sending.
Sir,
out,
when
I'm going to ask about the assignment.
no, sir, on the algorithm.
Go ahead.
Sir, when EFV is greater than 0 and there's no node to push there's no node W. So then we relabel the height, but the flow is still greater than 0, right?
Yeah, when we
So
relabel the height, we don't change the flow.
right. So at the end, the excess flow will not become 0 for this
It will
vertex.
become 0 because now that we have relabeled, then we go again, right? Then we go, so here we relabel and then we go to the start of the while loop. Now this V will still have access greater than 0.
Yes.
This is one such V. Maybe we can push now because now V has reached above.
Okay. Because of the height condition between V and W.
Exactly. Now the height condition has changed.
Okay. Now there will be new W, so we can push them. Okay.
Exactly.
Okay.
Any other question?
Sir, it is a question unrelated to the course.
Go ahead.
Sir, there is a course MAL 760. It is listed as a department elective in the courses of study book, but it is showing up as an open category code. So we just want a clarification if it is going to be a department elective or an
What is the
open
course?
category.
What is the name?
MAL 760. It's the one you're taking.
Can you tell me the course name? MAL.
Yes, sir.
Is that computing laboratory? No, that cannot be 760.
So that is MAL 760 is advanced algorithms, right?
Oh yeah, advanced algorithm. I'll be taking with Minati in the next semester. Yes, that's correct. So I don't know. So please send an email to I'm not sure. You can send it to Minati. You can see. So she's the coordinator of the course, and you can CC it to me also. But I'm not sure about these technicalities. So yeah. Send an email and we'll figure out somewhere.
Okay, sir.
Okay. Cool. Anything else? Anyone? Okay. If not, then see you tomorrow. Thank you for coming. Okay. We'll finish off flow push tomorrow. Thank you.